and that worked. Look at that. They were right after all that. First, turn it off and turn it back on, and after that, are you sure it's turned on? That's usually the two pieces of advice about all computers. All right, so chapter 12 is talking some more about solutions. Right, so most of the chemical reactions we deal with take place between either ions or molecules dissolved in water or dissolved in some other solvent. And we talked about this chapters and chapters ago, right? A solution is a homogeneous mixture of two or more substances, all of which have to be in the same phase. So you could have, right, salt dissolved in water, and now they're all in the same phase, right? You have aqueous salt dissolved in water, so they're all in the same phase. You could talk about, we don't usually talk about it in this way, but air, right, is a solution of a variety of other gases all mixed together into one big gas. We don't usually call air a solution, but it is a mixture of substances. They're all gases, all mixed together. So when we talk about solutions, we are concerned with what is going on at the molecular level, and then how do we know how much we have of all the different components in the solution. So, right, we've talked about intermolecular forces, that all liquids and solids are held together by a variety of intermolecular forces. What is an option of an intermolecular force? We know a bunch. Yep, dispersion force is an option. We got dipoles. Ion dipoles, yeah. We got some hydrogen bonding. Those are all good options. And then the other one, which, right, falls into a different category, we have our covalent bonds, attractions. And I guess we could also use ion-ion attractions. And dispersion forces are sometimes called van der Waals forces, just depending on which textbook you're looking at. Same thing. So we are examining a solution. We have to consider 3 different types of interactions. So we have all these types of attractions, but we want to look at the interaction between the solvent and the other solvent molecules. So let's say we have water, we have our salt and water solution. We're going to be concerned with how is the water interacting with other waters. What most likely of our list over here is going to be affecting our waters, affecting other waters. Excellent choice, hydrogen bonding. Good. Water interacts with itself mostly through hydrogen bonding, right? So all the waters are hydrogen bonding with other waters. We have the water interacting with the ion, right? So our solvent-solute interactions. So if I have sodium chloride floating around in there, what would be an interaction between the sodium and the chloride? Right, those are ion-ion interactions. Then, oh yes, so this is water. This is ion. And the one we most often talk about is how is the solvent interacting with the solute. So how is the water interacting with the ion? So those could be ion dipole, depending on what solvent, if this specifically is going to be an ion dipole interaction, right? The salt interacting with the water as a dipole. All right, I'm going to, if you have notes, just go ahead and cross that out. I was going to talk about that, but I'll talk about some other stuff. All right, so there's 3 types of interactions that are going on in a solution, each of which have different intermolecular attractions going on. They could all be the same, but most likely there's some combination. So let's talk about dissolving a solid in water. So I have calcium chloride dissolving in water. So if I have calcium chloride solid, how many calcium ions do I make when it dissolves? Okay. What would be the charge on the calcium? Oh, I already gave it away. How many chlorides? 2. So how many ions altogether have I made from dropping 1 calcium chloride in there? Right, you make 3 ions for every 1 molecule. And you make all right, we're going to make 2 chloride ions for every 1 calcium chloride. Seems obvious now that we're talking about it, but when we do some problems later, you'll have to remember that we put in 1 molecule of this, we get out 2 chloride ions. So that silly stoichiometry comes back to get you. All right, then just some other definitions that we've kind of talked about before. Saturated, which is where you've dissolved the maximum amount of solute into your solvent. You've probably experienced this. Does anyone actually ever make Kool-Aid anymore, powdered Gatorade? A few people, right? There's a limit to how much you can actually add before it just ends up being kind of sludge on the bottom, right? As much as you stir, there's still going to be that kind of sludginess on the bottom. You've made your saturated solution, so there's a limit to how much solid will dissolve. And the solubility is going to be the measure of the solute in equilibrium with the undissolved solute. So the solubility is a measure of how much solid can dissolve in a solution. So let's talk about some of our units of concentration we're going to use for this. So we've used molarity up to this point, right? Molarity in the units of moles per liter. Right, that's all we've used so far. Another way to measure concentration is to use molality, which is given the symbol little m, not to be confused with meters or metric or mass or any other word that starts with an M. I don't know why they didn't choose a different letter. They went with little m. So molality is moles of solute per mass of solvent. So let's describe in words. So in lab, probably like 2 weeks ago, right, you were making your vinegar solutions. So you took your 25 mils of vinegar, pipetted it into the volumetric flask. How much water did you have to add? Did you measure water to add, or you just dilute to the line? Dilute to the line. So do you have any idea of how much water you added? Not really. You have a ballpark guess. Like if you put in 25 and you know that's 100 total, it's probably 75-ish. But it doesn't tell you the exact volume of liquid that you added. Molality tells you the exact amount of liquid to add. So they'll always be similar, but one is considered more exact in terms of how much solvent to add. So let's take a look at this and see how it works. So I have a potassium chromate solution with an undetermined concentration, but Yeah, sorry, these are two questions. Not to be confused. But I know that I put in 38.3 grams of potassium chromate, and I put into and I combined that with 1 kilogram of water. So the question is, I want molality, which again is moles per kilogram. So what's the first thing I need to do in order to figure out this molality? I have to figure out how many moles. Clearly that decimal point's in the wrong spot. It should be 194. 19 doesn't make any sense for that mass. So once I figure out the moles, how do I turn it into molality? Right. And it has to just be the worst unit designation ever, because it's 0.197 m, not meters. Molality. Could be very confusing. Hopefully the context clues of the question let you know that we're measuring a concentration, not a distance. Hopefully the question isn't written so terribly. You're like, I don't know if they're asking for distance or concentration. I have no idea. Hopefully that won't happen. All right, so then let's do our more challenging question. Calculate the molality of a liter of a 1.22 molar sucrose solution. So this is really a conversion question. It's in units of moles per liter, and I want to get into units of moles per kilogram. So I have this. I have 1.22 moles per liter of sucrose, and I want to get that into moles per kilogram. So what is the first step I probably need to do? Well, it's already in moles. We know how many moles of sucrose are in there. We just know it's in a liter. But I want to change that liter into, I can do it into milliliters, okay? Okay, so now I'm in moles per milliliter. Use the density. All right, now I'm in units of moles per gram. So that's the last step I need to do. All right, let's see how that turns out. And we would expect them to be close, right? Because the density that we're using is not that far away from 1. And so I get a molality of 1.09. So again, these conversions you shouldn't be making a crazy different number. Just turning moles per liter into moles per kilogram. I don't know when you'll ever run into molality other in Gen Chem, but now you know what it means. So there's my community service announcement for the day. Let's do one other review question. The only other thing that I want to cover out of Chapter 12 is just a review of mole fraction. Where did we last see mole fractions? In gas laws, right? When we're looking at partial pressures, we had to deal with mole fractions. So just as a good recap, mole fractions is the amount of the component you're interested in divided by the total amount of the components. And these are all moles. So, super easy question to kind of get us geared up for our group quiz. I have a solution that is 1 mole ethanol and 9 moles of water. First, baby question, how many total moles are there? 10 total moles. So what is the mole fraction of the ethanol? 1/10. How about the mole fraction of water? We're good. That's it. That's mole fractions. We are done with all my lecturing. You can save your tears till afterwards. I'm a sympathetic crier, so if you cry, then I cry, then it gets all embarrassing. So don't, save it for later. Save it for your room.